radical with something raised that it converts over to this. So whatever the root is goes in the denominator, whatever the power is goes into the numerator. And I'm using this property if you just want to see it. This is just the way we convert from rational exponents to radicals. That's the exponent property, radical conversion. Okay, so you did that first.
Yep.
So now you have x to a power.
Yep. Raise it by 1, so it'd be 7/5.
Okay, so you're going to do, what about the 4?
Leave it.
Just leave it. So bring that here times, I'm going to leave a space here, x, and then you're going to add 1 to this.
Yep.
Okay, I'm going to do that kind of, I'm going to write it down before I do it. And then over here I'm going to have 1 over
2/5, so it'd be 5/2.
So this same thing, right? You still have to add them. So I'm just going to write 2/5 plus 1. So we haven't done the arithmetic. If you want to, if you can do it in your head, do it in your head. But I'm just saying that's like, mechanically, that's the formula, isn't it? This is, the constant comes for the ride. This is 1 over n plus 1 x to the n plus 1. 1 over n plus 1 x to the n plus 1. All right, now we have to add the fractions. So 4, oh, I forgot plus c. Okay, so now we do 4 times now 2/5 plus 1, 7/5. And then x to the 7/5, and then plus c. And we don't want to leave that 1 over 7/5, right? We want to just reciprocate it. So this will become 4 times 5 over 7, x to the 7/5 plus c, 20 over 7. So just multiply that 4 across the top. 20/7 x to the 7/5 plus c. Are there any questions on that? I'm going to move on to another one. Get used to adding 1 to fractions. Get used to this. This is going to be something you want to be able to do in your head. This to here, I'll show it once and once only. 2/5 plus 1 is the same as 2/5 plus 5 over 5, common denominator. Since they have the same denominator, you add the numerators up, 7, keep the denominators same. There you go. That's how we add, that's how we add 1 to a fraction. All right, next one. 4 over the 5th root of x squared. This problem's a little different. Priscilla, would you agree? It's different?
Yes.
Okay, what's different about it?
That it's a fraction.
It's a fraction, okay. So how, if even possible, how could you maybe attack this with the power rule over there?
We'll get it out of a fraction.
Okay, how would you do that?
Bring the denominator to the top.
Okay, so how about I rewrite it first like this? That's called rational exponents. So we convert the radical over to rational exponents, and now we bring it up.
Right.
Okay, I think that's what you're saying, yes? And when I bring it up, it's going to be negative 2/5. And now we can use the rule, right? Okay, so let's do that. The antiderivative of this will be, Priscilla, go ahead.
It would be, we leave the 4 alone.
Okay, so 4 is coming.
So times, and then it would be 1 over negative 2/5 plus 1
Good.
times x.
Yep.
And that would be negative 2/5 plus 1 plus c.
Good. Perfect. That's it. Right? So now we just need to figure out what those numbers are. Clean things up and we're done. Okay, so we've got to add those together. We've got to add those together. And these are going to be the same numbers, aren't they?
Yes.
Okay, so what is this?
So it would be 3/5.
3/5. So 1 over 3/5. X to the 3/5
Plus c.
plus c. And you always want to flip that up or like reciprocate it and multiply the 4 through.
So it would be 20 over 3.
20/3
X times to the power of 3/5 plus c.
plus c. There we go. That's it. And you can always check your answer, right? I mean, that's the great thing to remember. You can always check your answer. Take the derivative. You better get back, well, we would want to get back that, wouldn't we? And then we could always convert it all the way back to this. Questions on that? All right. James S. So James, I'm asking if you can come up with a function that when you take the derivative of it, you get 0.
I believe it would be f(x) of c. Something along those lines in order to get 0.
What do y'all think? That is correct. That is correct. Any constant. Any constant. Because if you have a constant by itself and you take its derivative, you get 0, right? So the antiderivative of 0 is a constant. We don't know which one, doesn't matter. There's an infinite number of them, right? Can y'all visualize what this family looks like?
It would be the whole number line?
It could be this, but it could be any constant, right? It's all these horizontal lines. And what do they all have in common? The slope of the tangent line anywhere on those lines is always 0. Right? Doesn't matter where you go. Go to any point on any of these lines, doesn't matter where it is, slope is 0 always. Good. All right, let's look at the next example. Now I'm going to put something up here in red because it's not correct. I don't recommend you write this down. I hate showing mistakes, but I just want to see what you think of this and tell me who wants to tell me what I just did? I'm telling you that, I'm saying that this might be the antiderivative.
The antiderivative of each part.
Yeah, I just did the antiderivative of each one, didn't I? I said, okay, what's the antiderivative of x? Well, that's x to the first power, so I did 1/2 x squared. This one was a little more involved because that's x to the 1/2, so I had to like add 1 to 1/2 and got 3/2 and then reciprocal out front. I did that in my head, but I should be able to, right? And then this one, x cubed, right? Do y'all agree with that? And then this one, this. Now, why doesn't that work? Well, we could check it. How could we check it? Take its derivative. And the problem is, if I ask you to take derivative of this, you have to use what? The quotient rule, right? And I guarantee you that if you take derivative of this using the quotient rule, you will not get that back. Okay, you won't. So up to this point, I have carefully avoided anything that's going to have quotients or products in them, because undoing those is very difficult. Right? That's what we're going to spend the next couple of weeks on, is how do you undo things that are multiplied or divided. But because this problem was very specially crafted for you, there is something you can do that will make it a little bit easier and manageable. But I had to make it a certain way. James, do you have something to say?
No, I'm just saying, yes, I got it.
So do you want to share what you would want to do?
Can you just split them up?
Yeah, we can just split this up into 3 separate terms. Because we have a single term in the denominator and 3 separate terms in the numerator, we can separate this out to be x over x cubed. Now I had to very specially make this. I mean, I had to leave this as a single term, didn't I? And then we could do minus the square root of x over x cubed, and then plus 3x squared over x cubed, right? That we could do. I agree with that. James, what would you do at that point?
Start reducing.
Start reducing, simplifying these, right? There's like x to the first over x cubed. This one is really like x to the half over x cubed, and then this one, I should be able to figure that out, right? And we just use the property that you subtract exponents. So I haven't done any antiderivatives yet. This is just algebraically kind of massaging this into something else. So what do we get here? 1 over x squared, which I'm going to write as x to the negative 2. And the reason I want it to be that is because then I can use a power rule on it, right? Okay, what about this one? I have to take 1/2 and I have to subtract 3. Negative 5 halves. So I'm going to get minus x to negative 5 halves. The minus comes from here. 1/2 minus 3 gives you negative 5 halves. Boom. And then what about this one? Plus 3, and then x to the negative 1, right? But you have to remember, x to the negative 1 was that special one that we can't use the formula on, right? So I'm going to, instead of doing that, I'm going to write it as 1 over x next to 3. 3 times 1 over x. I'm only doing it on this one because that's the special one. And now we should be able to do those term by term. Let me say that again. Do you remember in Cal 1, if you had terms and you differentiated, you could do it term by term. Antiderivatives work the same way. You can do them term by term. So let's start plugging in here using our power rule. So here n is negative 2, so I need to add 1 to that. So I get 1 over negative 1 x to the negative 1. Minus, okay, 1 over, okay, so I have to add 1 to that power, right? What happens when you add 1 to this? What do you get? Negative 3 halves, or negative 3 over 2. So that goes down here. X to the negative 3 over 2. And then plus 3 comes for the ride. Antiderivative of that, natural log of the absolute value of x, and then plus c. And then I'll just kind of clean this up. This, you can leave it as a negative exponent. There's nothing wrong with this. I could just leave this as negative x to the negative 1. This I would like to change to plus 2/3. So flip that, 2 negatives become positive. This I'll leave it as a negative exponent. And then this one, like that. Okay. That seems acceptable. There's no rule here in Calculus 2 that says you can't leave a negative exponent. That's like an algebra thing. I don't know. It's not a rule. This is still correct. All right? Yes?
Wait, so since we do it like term by term, wouldn't we have to like do like plus c for each?
Good question. The question was, since we're doing these one at a time, right? Then wouldn't we have to have like a plus c for each one? The answer is yes, but if this has a plus c and this one has a different plus c and this one has a different plus c, we're going to wind up adding all those plus c's together, right? And at the end, you're just going to have plus some constant. Still don't know what it is, right? It's a family of things. So having one plus c on the outside is sufficient. Yeah. Okay. Ready for the next one? right, so this is a bit of a tricky problem. So this problem, I don't expect people to get this, but it's to really point out that you can't do what we just did a second ago because you have more than one term in the denominator. Now, I know in my Cal 1 class we did do this problem, so I'm thinking maybe someone will know, but did anyone have an idea of what to try? What do you got, James?
Because it's over 1 plus x squared, you need to use trigonometry or take a derivative of a trig function.
Are you thinking like that arctan that I told you to put a star next to?
Something
Is that kind of what's going? Do you all see that 1 plus x squared on the bottom is there? So let me rewrite this for a second. What is going on? It's like 50-50 on these markers, whether or not they work good out of the box. Could I could I rewrite this like this? Could I? Is that correct? Yes. Where did my marker go? Maybe this is it. That is correct, but are you allowed to then just take the antiderivative of this one and this one separately? No, because in Cal 1 you couldn't even take derivatives of products separately, could you? You could not, like if I asked you to differentiate this, you'd have to use a product rule on this. So if I asked you to take the antiderivative, you definitely cannot do them individually. I always tell my students, if the product rule and quotient rule didn't exist, if they were what you hoped they were, right? Remember in Cal 1? The derivative of the product of two functions is this product rule, right? It is not equal to that, right? I always tell my students, if this were true, we'd have a lot of people doing calculus, right? Because this is, I mean, like it wouldn't be as hard of a class. Same with the quotient rule. But because this is not true, it's this, it makes taking derivatives of products much harder. And so when we try and go backwards, it's going to make it, well, really, really hard. Really hard. So we cannot do these separately at all. Okay, if we can't do them separately, then maybe that's not the path. So does anyone have a suggestion as to what to do here?
Multiply out the 1 over 1 plus x squared. So
What do you mean multiply it out?
it'd be 2 over 1.
Oh. Are you wanting me to rewrite it like this? I don't know if this is what you're wanting me to do.
Kind of.
Is that legal algebraically? Is this okay? So algebraically, that's okay. Algebraically, right? But we can't do anything with it. We can't find the antiderivative of these separately. So even though algebraically this is right, can't do anything with it. Algebraically, is this the same as the original? Yes. Can you do anything with it? So on this one, look at this one here. Isn't that 2 times 1 over 1 plus x squared? Isn't that what that is? Okay, that's a constant. It can come for the ride. This, do you know the antiderivative of this? Arctangent of x. We actually can get that piece. Do you all see that? And then we have addition. So plus, now we just need to figure out what that is. But that's a problem. Because that has an x squared on the top. And you cannot do that the same way. Why can't I do this one this way? I was able to do it this way, but I couldn't here. That's not a constant, right? Constants come for the ride. Functions of x do not. So you cannot just do, x squared and then arctan. You can't do it. So we're still stuck here. What's that? Can you do x squared over 1, x squared over x squared? No. That's bad. That's bad, right? That algebra does not exist. Okay? If it were flipped over, you could. One term on the bottom, 2 on top, you can split it. But I mean, we're kind of stuck here. Like that's okay, but that's not. All right? So y'all ready to see how to do it? Okay. There's 2 ways to do it. Might be more, but I'm going to show you the ways that you can get to this answer. Okay, here we go. Okay, long division. Start with long division, all right? And the way you do this, you make sure you put the numerator in the box and denominator outside. Make sure you're in descending order. Normally, I should leave spaces in here. Like if I'm normally doing long division, I should leave a space for the x term. Let me go ahead and do that. Since there's no x term, put a 0x here and then plus 2. And now what you do is you say, all right, what do you multiply x squared by to get x squared? 1. So I put a 1 up here. Doesn't matter where you put it. I know some professors are like, well, go line it up. It doesn't matter. Just 1. Then you multiply 1 times this, and put those underneath. So 1 times x squared, that goes here. 1 times 1, that goes underneath the 2. And then subtract it. So subtract this line. So minus, this becomes minus, this becomes minus. Now you add straight down. What do you get when you add down? Gone, gone. This isn't even here. You get a 1 here. And then you ask yourself the question again, what do I multiply x squared by to get 1? And this is where you stop, because you can't turn x squared into 1. So this is your remainder. So what you put here is plus, and you put your remainder up here, and you put your divisor underneath it. That's long division. If you need to, go back, go to the tutoring lab, come into my office. We can do a bunch of long division problems. Long division is going to be with us. It's not going to always be here in this class, but it won't ever go away either. Like we will just pull it out when we need it, all right? And this is a simple long division problem. This is not complicated at all. So if this is kind of tripping you up, make sure that you go get refreshed on that. Okay, so what we're saying then is that this expression, right, is equivalent to that, right? 1 plus 1 over x squared plus 1. They're equivalent expressions. And because they're equivalent, now I can integrate that, or sorry, I said integrate, sorry. I can find the antiderivative of that, of each one separately now, can't I? Because there's addition between them now. So there's a nice, clever way of turning this quotient into a sum. And fortunately for us, this one, we know how to do. So the antiderivative here would be, let's see, antiderivative of 1, just x, plus arctangent of x plus a constant. There we go. There it is. Uh-oh, sounds like code red there. You all right?
Yes, sir.
Any questions? That's the first way. Here's the second way. And I actually think the second way is not... The second way is one of those things where I'm going to show it to you and you're going to go like, why? Like, where would I ever have thought to do that? And then I'm going to tell you because I just showed you, and like someone showed me, and now you know, you're in on it now, right? Like you know that these little tricks exist. So here's the trick. Do you agree that this is the same thing? Is 1 plus 1 plus x squared the same as 2 plus x squared? Yeah? So can't I then do like 1 over this plus these two over this? It's like I'm splitting it into two pieces. I'm going to go 1 over that, and then I'm going to do that over that. And what do I get on that second one? That's just 1, right? So this is just 1 plus 1 over 1 plus x squared, which is exactly that. So I actually got to the same thing without doing any long division. Now you cannot do that all the time. It just, for this particular problem, it worked out. That's kind of clever and tricky, isn't it? Okay. All right, I've got about 12 minutes or so. Y'all doing all right? Okay. See where we are in terms of these notes. Yeah. All right, so remember now from Cal 1, hopefully you talked about this in Cal 1, that if, okay. I thought I've got this here and sometimes I question it. Okay, so in Cal 1, hopefully you learned that if you're given a position function, S of t, S equals f of t. If this gives you position, the position of an object moving in a straight line, so it's giving you the distance something has traveled in a straight line as a function of time. So if you're given that, then the first derivative of that would give you the velocity, and the second derivative would give you the acceleration. Did you all learn that in Cal 1? Yes. Okay, so this is just reminding you. If you're given a position function, then the velocity function v is just the derivative of that position function, and the acceleration function of that is just the second derivative. Okay? That means that we can look at this backwards. If we start with an acceleration function, the antiderivative of that should be the velocity, and the antiderivative of that should be the position. Do you all agree with that? Okay. So if we have some function, forgot the letters we used, S, this is your position function, then if we take the derivative, so I'm put diff for differentiation, if we differentiate that position function, we get velocity, and that'll be some other curve. And then if we differentiate that velocity function, we'll get another curve, whatever that looks like, and that'll be your acceleration. So starting with this, if I gave you a position function, you should be able to tell me exactly the acceleration function, right? And what I'm saying is if we start with the acceleration, we should be able to get back to the position. But there's going to be a catch with that. What's the catch? What happens? Every time we go back, right? If I go from here, antiderivative to here, it's some function plus c. So it's an infinite number of answers, right? It's a family. And then if we try and go back again, now we have each of those family members here has its own family, right? So we have like an infinite number of possibilities, don't we? Okay. 10 minutes. I'm trying to debate how I want to go about this. I think I can probably finish this off with some examples next class. I want to show you just a quick application, not application, but I just want to show you something cool with this. How many of you remember seeing this somewhere in college algebra, something like this? It may not be exactly this, or maybe in physics. Anyone remember seeing that in physics? This tells you, this gives the height of an object in feet after t seconds. So this has to do with falling objects on Earth. With no air. If you take out the air resistance and you just take something and you drop it on Earth, it's going to fall, right? And this function right here will give you the position, how high it is off the ground after so many seconds have transpired. Does that at all look familiar? Just raise your hands if it does. Just a few of you maybe. Okay. So I would like to explain what's happening here. With this formula, d sub 0 is always the starting height. That's where you're dropping, how high the object was when you dropped it. And v sub 0 is what we call the starting velocity. So when you have an object and you're going to drop it, if I just let it go, then however high it was, that's d sub 0, that's d naught. And if I just let it go, then v naught is 0 also. But I can also take it and throw it down, or I could have taken it and thrown it up. So if I give it some sort of motion up or down, then this will be a number other than 0. All right? So this formula is used in physics and in college algebra, sometimes you look at it as an application. I'm actually going to show you now where the formula comes from, all right? And we're going to use this right here. So we would like to get to, this is a position function, all right? This gives you the position. I'm trying to figure out where it came from, this formula. So let's see if we can get it by starting out all the way at this end. Acceleration. So when you drop an object, the only force acting on that is what?
Gravity.
Gravity, right? And gravity, the acceleration of gravity is what?
9.81 meters per second squared.
9.8, however far you want to go with that, meters per second squared, right? Y'all have heard that? If we convert that into feet per second squared instead of meters per second squared, we get, and we're going to look at acceleration down as being negative. So we're going to say negative 32 feet per second, all right? So the acceleration at any point in time of an object that's dropped on Earth is negative 32 feet per second squared, all right? That's meters converted over to feet, all right? A little bit of rounding, but we're close enough. All right, you with me? All right, let's see if from that we can get to this position function. So let's find the antiderivative of this. If we find the antiderivative of this, that'll give us our velocity function, won't it? Okay, so the antiderivative will be velocity function. And what it should be is the antiderivative of the constant negative 32. What's the antiderivative of the constant negative 32? Negative 32x, but what's our variable here? T, right? So the antiderivative of that will be negative 32t plus some constant, right? Would you agree that this constant right here is how fast we're traveling at time equals 0? So look at this expression right here. If I asked you right now to tell me how fast, what's the velocity at time equals 0, plug that in here and what would you get? C, right? So this number right here, C, let's call it something. It's the starting velocity, right? Let's call it v sub 0, right? Okay, so I'm going to rewrite this. Negative 32t plus v sub 0. All right, we don't know what it is, do we? We don't know what the starting velocity is. But that's okay. Let's integrate again. I said integrate, sorry. Let's do the antiderivative again to get to position, even though we don't know what this is. So the position function, which I'm going to call d of t, should be the antiderivative of this. So what is the antiderivative of negative 32t? And our variable here is t, right? So negative 32 comes for the ride. Times, and now t, you're doing the antiderivative of t to the first power, which gives you 1/2 t squared, right? And then plus, what is the antiderivative of a constant? That's the derivative, the antiderivative of the constant. The constant times t, right? So v naught t, and then plus some constant, right? Plus c. Let's not use c, let's use a different one. Let's use d, all right? Do y'all agree with that? Does that look a lot like this? We do have negative 16t squared, don't we? We do have v naught t, right? Then we have d naught instead of capital D. But what is capital D? I mean, look at it right here. If you plug in 0 into this, right? That's supposed to give you, at time 0, it's supposed to give you the position, isn't it? And this, if you plug 0 in for t, goes away. This goes away, and all you get is d, don't you? So that capital D is always going to be your starting height. So let's call it this. And so there you go. There's your formula, right? And that's the formula you have for any object falling on Earth. What I'm getting at is if you know the acceleration of gravity on whatever planet it is you're on, no matter what planet it is, you're always going to have a quadratic function that models how fast something falls. Always, it will always be quadratic, as long as your acceleration of gravity is constant. If your acceleration of gravity on the planet's changing, then that would be a very interesting planet, wouldn't it? It's like you move over here, your gravity is different than your over here. Yeah, I mean, but it could be, right? But as long as your acceleration of gravity is constant, then you can always model the position of something after a certain amount of time as it falls on any planet with a parabola. A parabola. Because you're going to integrate a constant twice, which takes you up, the power goes up twice, right? Okay, so do what you can on your homework. Definitely you should have 3.5 and 3.6 done. You should try and do everything for 4.7. Where's my book? Let me see if there's anything on 4.7 I think you're going to have trouble with. So I think you're going to start running into some issues. On 4.7, you're going to start running into issues, I think, once you get to like problem 23. Because we haven't quite talked enough about that. And you're supposed to do 23 through 33. So there's about 10 problems there. Well, your assignment's 1 through 33. And then 2 other problems. But you should be able to do the first 22, 23 of those. You should be able to, in theory. But I do think you might struggle a little bit with 23 and on. But I will clarify that come Tuesday. All right, we're good? Have a good weekend, everyone. Pardon?
All the practice questions, 3.6.
3 points. What about 3.6? What are you asking about 3.6?
It's all the questions in the book.
No. This calendar is online under files.
Oh, okay.
Yeah. So you just go to the book and you just correspond the page and you have the book? Huh?
Yeah.
Yeah. Okay. So just do the problems that are assigned here. Okay.
Thank you.
Yes.
Do you take attendance?